In this lesson, we're going to talk about the vertical angles theorem and how to prove it and use it. But before we do, we have several vocabulary terms that we need to go over. Some of them you may be familiar with, and others may be new to you. So let's talk about labeling angles first. Remember that we are going to we have options for labeling them. We can label them the three ways that are listed down here. I could label them with all 3 points right here, but remember when I do that, my vertex has to be the letter in the middle, so notice it's angle ABC. I could also label it CBA, but as long as I put the vertex in the middle. I can also just label the angle with the vertex letter. However, you need to be careful with this because it can lead to confusion, especially if I have, let's say, adjacent angles. So if I have something like this, and this is A, B, C, let's just say X. If I say angle B and just use one letter, I don't know what angle you're talking about. I don't know if you're talking about this portion, this lower portion, or the entire thing. So in this case, you would definitely want to use 3 letters to name it. You can also use numbers to label the angles, and if that's the case, it's going to be a number that's inside of the angle. So for example, I could put numbers in here and then just refer to them as angles 1 and 2. Straight angles are angles where we have opposite rays that go in opposite directions. So remember, ray begins at a certain point and then extends infinitely in one direction. And then here's another ray, it begins at a point and it extends infinitely in the opposite direction. So straight angles basically are straight lines. And straight lines are something that we can assume from a diagram. If a line looks straight, we can assume that it is straight. We don't need to be told that it is straight. And then again here we can see that it's not straight. Adjacent angles are angles that lie next to each other. They share a vertex and a common side. So here would be an example of adjacent angles. So they share the vertex B and they share this common side BC. Non-adjacent angles, they don't have a common vertex or a common side, but they have shared interior points. So here we would say that PQS is not adjacent to the entire angle PQR. They're not adjacent because they share this interior point of S. Now PQS is adjacent to SQR, but I was referring to what it talks about right here, which is this angle compared to the whole angle. So remember, adjacent is those that are right next to and share a vertex. Linear pairs are pairs of adjacent angles whose non-shared side forms a straight angle, meaning I've got adjacent angles right here, and my non-shared side, this is my shared side, so my 2 non-shared sides form a straight angle. So basically I have adjacent angles that form a straight line. Vertical angles are non-adjacent angles formed by 2 pairs of opposite rays. So basically make an X, and then these would be these would be the vertical angles. So this angle is labeled as well as this, that they are congruent, and then opposites. So again, vertical angles are congruent. The angle addition postulate is pretty much common sense, but basically it's saying that if I have a large angle here that's made up of 2 smaller angles, let's call it angle 1 and angle 2, then the entire angle is equivalent to angle 1 plus angle 2. Yes, so again, pretty straightforward on that one. Supplementary angles, again, this should be review, but 2 angles whose sum is 180. That doesn't necessarily have to be a linear pair. I can have an example like this, that they are a linear pair and these two angles are supplementary. But I can also have an example like this where they just add up to 180, but they're not necessarily connected, or they're not, they don't form a linear pair, so they're non-adjacent. If two angles form a linear pair, then they have to be supplementary. We talked about these congruence properties with segments, but they apply with angles as well. So we have the reflexive property that any angle is congruent to itself. Symmetric property, basically we can flip it around and the order doesn't matter, it's still congruent. And then the transitive property, remember, if 1 is congruent to 2 and 2 is congruent to 3, then 1 and 3 have to be congruent to each other as well. This theorem basically states that if these two angles add up to 180, and these two angles add up to 180, we've got angle 2 being the same right here. So let's say angle 2 was 50, right? Well, then that would leave angle 1 and angle 3 to have to be the same measure, because it's 180 minus whatever that angle 2 was. So if angles are supplementary to the same angle, then they are congruent. Perpendicular lines, if I have two perpendicular lines, then they're going to form four adjacent congruent right angles. Now notice that it's just labeled with that square there. You could put them all, but you really only need one, and that's going to show that they're all perpendicular. Remember, this is my symbol for perpendicular, basically an upside down, if I can get my pen to work, upside down capital T, and that's my symbol for perpendicular. So in my diagram, these two lines, which technically I should have these over them, those are showing that those are lines. So I've got SQ and PR, they're perpendicular, so SQ is perpendicular to PR. Rays and segments can also be perpendicular, so I could have a ray perpendicular to a segment, or two rays perpendicular, two segments perpendicular, as well as lines. Perpendicular bisectors, they're both, so they're perpendicular and they bisect. Remember that in order to bisect, it has to be a segment. So I cannot cut a line in half because I don't know where it begins or where it ends. But a segment, I do know where it begins or where it ends. So if it's a perpendicular bisector, it cuts it in half. That would be the bisect part, right? And then it's perpendicular. Now, what is bisecting it and what is perpendicular to it, this could be a line, a segment, or a ray. But the actual one that's getting bisected has to be a segment. We have a theorem, the perpendicular bisector theorem, that says any point along the perpendicular bisector, so here's my perpendicular bisector, any point on this line, on this perpendicular bisector, is equidistant or the same distance from the endpoints of the segment that it bisects. So basically these dotted lines right here are congruent. If I picked another point somewhere on my perpendicular bisector, then this distance and this distance would be the same. Anywhere I pick along there, the distance from that point to the ends of the segment that got bisected are equidistant or are congruent. Complementary angles, we talked about supplementary angles, angles that add up to 180. Complementary angles are two angles who add up to 90 degrees. They can form a right angle like this right here, and so they're adjacent, or they can be non-adjacent and they're just complementary because they add up to 90. So let's look at a couple of examples, including a proof. Here we want to look at listing the pair of supplementary angles, the pairs of vertical angles, and a pair of opposite rays. So let's talk about my supplementary angles. Supplementary angles, remember, are angles that add up to 180. So based on my diagram, I'm going to pick the ones that form a straight angle. So 5 and 6 are supplementary. 1 and 2 are supplementary. 2 and 3 are supplementary. They form a straight angle. 3 and 4 are supplementary because they form a straight angle. And 4 and 1, as well as 7 and 8. So all of those pairs are supplementary. And then we have vertical angles. So these are not vertical angles, but these are. So 2 and 4 and 1 and 3. And then a pair of opposite rays. Notice that these are not rays because they stop and start at specific points, but these have arrows on them, so we've got rays or lines. If I start with B, that can be my end point or my beginning point, and I can go in opposite directions through A and through C. So my opposite rays would be BA, starts at B and goes past or through A, and then BC again starts at B and then goes past C. It tells me that AC and BD are intersecting lines, and it gives me the measure of angle 1 and 2. So I'm going to go ahead and label those. I've got 3x plus 14 and 9x plus 22. And it wants me to find angles 3 and 4. But basically, if I can find these, then we've got vertical angles for 2 and 4 and 1 and 3, so I can know what those are. These two angles are supplementary because they form a straight angle, which means that they have to add up to 180. So I've got 3x plus 14, add that to 9x plus 22, and that has to add up to 180. So I'm going to combine like terms. I get 12x plus 36 equals 180. 12x, if I subtract 36, 180 minus 36 gives me 144. And then divide both sides by 12 gives me 12. So x is 12. If I plug 12 in, 3 times 12 is 36, plus 14 gives me 50. And if this is 50 again, I don't have to substitute it in. I could, but if this is 50, then this one has to be 130 because they have to add up to 180. And then remember, vertical angles are congruent. So if this is 50, then angle 3 is also 50. This is 130, then angle 4 is also 130. So 3 and 4 was what I was looking for. Alright, proving that vertical angles are congruent given a pair of intersecting lines. So we're not just going to use that assumption that vertical angles are congruent, that theorem. We're going to actually prove that theorem. And this is we're going to do it as a two-column proof, but it's going to be a little bit more algebraic. Remember that with a two-column proof, we have our statements and our reasons. The first thing that we are going to start with is we're going to say that angle 1 and angle 2 are add up to 180 because we know that they form a straight line, and I can assume that they form a straight line. So the measure of angle 1 and the measure of angle 2 has to equal 180 degrees. Okay? My reason for that would be if two angles form a straight angle, then they are supplementary, and in parentheses I'm going to put add up to 180. Alright? So we know that's the case. Angle 1 and angle 2 add up to 180. 2 and 3 I also know add up to 180 as well. So the measure of angle 2 plus the measure of angle 3 is also 180. And instead of repeating myself, because I've given that same, it would be the same exact thing repeated, I'm just going to put same as number 1. pretty convenient. Alright, so I know that those two angles are both equal to 180. Or these two sums equal to 180. So if 1 and 2 add up to 180, and 2 and 3 add up to 180, then they must be congruent to each other, meaning that the measure of angle 1 plus the measure of angle 2 has to be equal to the measure of angle 2 plus the measure of angle 3. Because if these are each equal to 180, then they have to be equal to each other. So we've got the measure of angle 1 and 2 added together has to be equal to the measure of angle 2 and 3. And this basically, we just use the property of substitution. Alright, so my next reason is going to, my next statement is basically I'm going to subtract out that angle 2. If I subtract it from both sides, then I'm left with the measure of angle 1 is equal to the measure of angle 3. And I just used subtraction. And lastly, I know this is sort of repeating myself, but angle 1 then is congruent to angle 3. So basically here we're just saying their measures are equal, so we're being specific and saying they're congruent. And my reason for that is I'm just going to put since the measure of angle 1 equals the measure of angle, then angle 1 has to be congruent to angle 3. Alright, so that is not quite as formal as some of the ones we've done before, but nonetheless it has proven that angle 1 and angle 3 are congruent, which are my vertical angles. Alright, the last thing that we're going to look at is that perpendicular bisector theorem. Remember we said that if a point is on the perpendicular bisector, then it's equidistant from these two ends, so these are congruent. It tells me that AD is 4x minus 1, and DC is x plus 11, and it asks me to find the values of these. So I need to solve for x and then plug them back in. So I'm going to set them equal to each other because these two are congruent, so that means they must have the same measure. Solve, and I have 3x equals 12, so x is 4. And if x is 4 and I plug that back in, 16 minus 1 is 15. And again, if I plugged it in just to double check myself, 4 plus 11 is also 15.